All right, let's jump right in. Today, we're tackling a really fundamental challenge in engineering, something that seems simple but is actually incredibly tricky. How in the world do you measure something you can't see, that's always moving? We're talking about the flow of fluids, and trust me, it's way more important than you might think.
I mean, really, stop and think about that for a second. You've got water rushing through a massive pipe or a tiny amount of fuel being shot into an engine. You can't just stick a ruler in there, right? So how do you do it? This is the exact puzzle we're going to solve today.
And look, this is way more than just a neat science problem. Getting this right is absolutely critical for so many things we rely on every day. We're talking power plants generating our electricity, chemical factories making products we use, and even high-tech research labs. It all boils down to three things: efficiency, safety, and control.
So, here's our game plan. First, we'll look at the most intuitive idea: meters that have actual moving parts. Then we'll get a little clever and explore how you can use the power of pressure. After that, we're going high-tech with waves and magnetic fields. And finally, we'll wrap up with the most important part: how do you actually pick the right tool for the job?
Okay, let's kick things off with our first category, meters that move. This is probably the most straightforward way to think about the problem. Let's just put something in the path of the flow and see how it reacts. It's a simple, elegant, and often very visual solution. The core idea here is something called a variable area flow meter. Now, that sounds complicated, but the concept is super intuitive. Imagine you have a tube that's tapered, so it gets wider as you go up. As the fluid flows in from the bottom, it pushes a little object, or float, upwards. The more flow you have, the higher that float has to rise to find a wider spot where it can settle. Its height tells you the flow rate. Simple as that. And the classic example of this, the one you've probably seen in a lab somewhere, is the rotameter. It's exactly what we just described. Fluid comes in, the bottom of that tapered tube, it pushes the float up, and the float just hangs there, suspended in the flow, fighting against gravity. You just look at the side of the tube and read the measurement. It's brilliant. So, why are these things so popular? Well, for one, they're dead simple. Not a lot of parts to break. They work best with clean fluids, so the float doesn't get gunked up. You can get them with a clear glass tube so you can literally see the flow, or a sturdy metal one if you're dealing with something nasty. And here's a neat design tip. The longer the tube, the more sensitive and accurate your reading will be. All right, on to our next category, the power of pressure. So the moving parts are great, but what if you can't put a float inside your pipe? Or what if the fluid is too aggressive? Well, this is where we turn to physics. It gets really clever here, because we can use pressure differences to basically see the flow rate without any moving parts at all. This whole concept hinges on a famous principle called Bernoulli's law. Now, you can get deep into the physics, but the key takeaway, the only thing you really need to remember, is this: as a fluid speeds up, its pressure drops. That's it. So, if you create a little bottleneck in a pipe, the fluid has to speed up to get through it. By measuring the pressure before the bottleneck and at the bottleneck, that pressure drop tells you exactly how fast the fluid is flowing. And here are two perfect examples of that law in action. On one hand, you have the Orifice plate. It's basically just a metal plate with a precise hole drilled in it. It's super cheap and easy to install, but it creates a lot of turbulence, which means you lose energy in the system. On the other hand, you have the Venturi tube. It's this beautiful, smooth, tapered design that's way more efficient and loses very little energy. The catch, you guessed it, it's much, much more expensive. It's that classic engineering puzzle, right? Cost versus performance. Now for another genius pressure device, the Pitot tube. If you've ever looked at the front of an airplane, you've seen one of these sticking out. It's an L-shaped tube that points directly into the flow. It cleverly measures two things at once: the static pressure of the air around it and the total or impact pressure of the air hitting it head-on. The difference between those two pressures is directly related to the fluid's velocity. And here's what's just incredible about the Pitot tube. It's ridiculously robust. You think it has to be perfectly aligned with the flow, but it actually stays accurate even if it's off by as much as 16 degrees. Think about that. An airplane is bouncing around in turbulence, and this little tube is still getting a solid reading. That's why they're so reliable in the real world. Okay, time to move into the really high-tech stuff with our third category, waves and magnetic fields. So far, everything we've talked about has involved either putting something in the pipe or constricting the pipe. But what if you can't do that? What if you can't touch the fluid at all? Well, this is where we use sound and magnetism to measure flow completely from the outside. We're going to look at the two big players in this hands-off approach: ultrasonic meters, which, as you can guess, use sound waves, and electromagnetic meters, which use, well, magnets. Both get the job done without ever getting in the way of the flow, but they work on totally different principles. So let's break down how they stack up. The ultrasonic meter works by sending a sound pulse across the pipe, first with the flow and then against it. It measures the tiny time difference to calculate the flow speed. The electromagnetic meter uses a physics principle called Faraday's law. Now here are the crucial trade-offs. The electromagnetic meter is way more accurate, but there's a huge catch. The fluid has to be electrically conductive. The ultrasonic meter, on the other hand, is more forgiving about the fluid type, but it's less accurate and really needs the fluid to be clean and uniform. And this is the secret sauce behind that electromagnetic meter. Faraday's law is a fundamental rule of physics that says when you move an electrical conductor through a magnetic field, you generate a voltage. And here's the absolutely brilliant part of this invention. The moving conductive fluid is the conductor. How clever is that? The meter creates the magnetic field, the fluid flows right through it, and the tiny voltage it generates tells you exactly how fast it's moving. It's just genius. So we've seen it all, from a simple float in a tube to complex electronics that use magnetic fields. This brings us to the final and maybe the most practical part of our discussion: choosing the right tool. With all these options, how on earth do you decide which one to use for a specific mission? Well, it's all about playing a balancing act. You have to ask a bunch of questions. First, what's the fluid like? Is it clean or dirty? Is it conductive? Then, how accurate do you really need to be? Is close enough okay, or do you need pinpoint precision? Can your system handle the energy loss from something like an orifice plate? And of course, there are always the real-world problems. How much space do you have? And the big one, what's your budget? At the end of the day, the biggest takeaway is this: there is no single best flow meter. It just doesn't exist. That cheap and simple rotameter might be absolutely perfect for a small lab setup, but for a massive industrial plant, you're going to need something way more robust and accurate, like an electromagnetic meter. It's always about matching the tool to the specific job. And that leaves us with a pretty cool thought. Right now, all around you, these invisible flows are constantly being measured. The water coming into your house, the gasoline going into your car at the pump, the air circulating through the building you're in. It's all being watched and controlled. Now that you know how it's done, you can't help but wonder, what other invisible currents in your world are being made visible by these incredible devices?